Hello, welcome to the next section, data munging. In this section, you'll learn how to munge data. We start this section with the video Data Loading and Pre-Processing with Pandas. In this video, you're about to learn how to structurally load, manipulate, process and polish data using Pandas and NumPy. Let's start with the CSV file and Pandas. The Pandas library offers the most accessible and complete function to load tabular data from a file, or a URL. By default, it will store data in a specialized Pandas data structure, index each row, separate variables by custom delimiters, infer the right data type for each column, convert data, if necessary, as well as pass dates, missing values and erroneous values. You can specify the name of the file, the character used as a separator, the character used for the decimal placeholder, whether there is a header, and the variable names, using names and a list. The settings of the sep and decimal parameters have default values, and they are redundant in this function. Anyway, for a European-style CSV, it's important to point out both, since many European countries, but also in some Asian countries, the separator character and the decimal placeholder are different from the default ones. The resulting object, named iris, is a Pandas data frame. It's more than a simple Python list or dictionary, and in the sections that follow, we'll explore some of its features. To get an idea of its content, you can print the first rows using this command. The function, if called without arguments, will print 5 lines, and using this tail command, we'll get the last 5 rows. If you want to get back a different number of rows, just call the function using the number of rows you want to see as an argument, as shown. The preceding command will print only the first 2 lines. Now, to get the names of the columns, you can simply use the column attribute. The resulting object is a very interesting one. It looks like a list, but it is actually a Pandas index. As suggested by the object's name, it indexes the column names. To extract the target column, for example, you can simply use this line. The type of the object Y is a Pandas series. Right now, think of it as a one-dimensional array with axis labels, as we'll investigate it in depth later on. Now, we just understood that a Pandas index class acts like a dictionary index of the table's columns. Note that you can also get a list of columns referring to them by their indexes. In this case, the result is a Pandas data frame. Why such a difference in results when using the same function? In the first case, we asked for a column. Therefore, the output was a 1D vector, that is, a Pandas series. In the second example, we asked for multiple columns, and we obtained a matrix-like result. A novice viewer can simply spot the difference by looking at the heading of the output. If the columns are labelled, then you're dealing with a Pandas data frame. On the other hand, if the result is a vector and it presents no heading, then that is a Pandas series. So far, we've learned some common steps from the data science process. After you load the dataset, you usually separate the features and target labels. In a classification problem, target labels are the discrete or nominal numbers or textual strings that indicate the class associated with every set of features. Also, you need to know the size of the dataset. Typically, for each observation, we count a line, and for each feature, a column. To obtain the dimensions of the dataset, just use the attribute shape on both a Pandas data frame or series, as shown. The resulting object is a tuple that contains the size of the matrix or array in each dimension. Also, note that Pandas series follow the same format, that is, a tuple with only one element. Now, you should be more confident with the basics of the process. So let's see what happens if the CSV file contains a header and some missing values and dates. To make our example realistic, let's imagine the situation of a travel agency. This is the data. According to the temperature of 3 popular destinations, they record whether the user picks the first, second or third destination. In this case, all the numbers are integers, and the header is in the file. Let us load this dataset. Here, Pandas automatically gave the columns their actual name after picking them from the first data row. We first detect a problem. All of the data, even the dates, has been passed as integers. or, in other cases, as strings. If the format of the dates is not very strange, you can try the auto-detection routines that specify the column that contains the date data. We do it with these lines. Now it looks fine. Now, in order to get rid of the missing values that are indicated by NaN, which stands for not any number, replace them with a more meaningful number, let's say 50 Fahrenheit. After that, all of the missing data is no more, replaced by the constant 50.0. Treating missing data can also require different approaches. As an alternative to the previous command, values can be replaced by a negative constant value to mark the fact they are different from the others, and leave the guessing to the learning algorithm. NaN values can also be replaced by the column mean or median value as a way to minimize the guessing error. The .mean method calculates the arithmetic mean of the specified axis. That axis equals 0 implies a calculation of means that spans the rows. The consequently obtained means are derived from column-wise computations. Another possible problem when handling real-world datasets is when loading a dataset containing errors or bad lines. In this case, the default behavior of the load_CSV method is to stop and raise an exception. As an example, let's say that you have a badly formatted dataset, as the one shown here, and you want to load just all the good lines and ignore the badly formatted ones. Here's what you can do with the error_bad_lines option. As you can see, it skipped the third line. If the dataset you want to load is too big to fit in the memory, you can deal with it using a batch machine learning algorithm, which works with only part of the data at once. Using a batch approach also makes sense if you just need a sample of the data. Let's say that you want to take a peek at the data. Thanks to Python, you can actually load the data in chunks. This operation is also called data streaming, since the dataset flows into a data frame or some other data structure as a continuous flow, as opposed to all the previous cases, the dataset has been fully loaded into the memory in a standalone step. With pandas, there are two ways to chunk and load a file. The first way is by loading the dataset in chunks of the same size, as shown in this code. Here, each chunk is a piece of the dataset that contains all the columns and a limited number of lines, not more than is set in the function call, that is, the chunk size parameter. Note that the output of the read_CSV function in this case is not a pandas data frame, but an iterator-like object. In fact, to get the results in memory, you need to iterate the object. As you can see, there are 14 pieces, each of them of shape 10,5. The other method to load a big dataset is by specifically asking for an iterator of it. In this case, you can dynamically decide the length, that is, how many lines you want for each piece of the pandas data frame. In this example, we first define the iterator. Next, we retrieved a piece of data containing 10 lines. We then obtained 20 further rows. And finally, the 2 rows are printed at the end. Besides pandas, you can also use the CSV package, which offers 2 functions to iterate small chunks of data from files, the reader and the dictReader functions. Let's illustrate such functions by importing the CSV package. Here is a simple example that uses such functionalities from the CSV package. Let's pretend that our dataset-uci-iris.csv file that we downloaded from is a huge file that we cannot fully load in the memory. You can read from this link. Therefore, our only choice is to load it in chunks. Let's first conduct an experiment. This is our code. First, it opens a read binary connection to the file that aliases it as data_stream. Using the with command assures that the file is closed after the commands placed in the preceding indentation are completely executed. Then, it iterates, and it enumerates a csv.dictReader call, which wraps the flow of the data from data_stream. Since we don't have a header row in the file, field names provides information about the field's names. Dialect just specifies that we're calling the standard comma-separated CSV. Inside the iteration, if the row being read is just the first, then it's printed. otherwise the loop is stopped by a break command. The print command presents us with row number 0 and a dictionary. Therefore, you can recall every piece of data of the row just by calling the keys bearing the variable's names. Let's run it. Similarly, we can make the same code work for the csv.reader command. Here the code is even more straightforward, and the output is simpler, providing a list that contains the row values in a sequence. At this point, based on this second piece of code, we can create a generator callable from a for loop. This retrieves the data on the fly from the file in the blocks of the size defined by the batch parameter of the function. Similar to the previous example, the data is drawn out thanks to the csv.reader function wrapped by the enumerate function that accompanies the extracted list of data, along with the example number, which starts from 0. Based on the example number, a batch list is either appended with the data list or returned to the main program using the generative yield function. This process is repeated until the entire file is read and returned in batches. Such a function can provide the basic functionality for learning with stochastic gradient descent, as will be presented in Chapter 4, Machine Learning, where we'll come back to this piece of code and expand the example by introducing some more advanced examples. Finally, Pandas data frames can be created by merging series or other list-like data. It can be said easily that for each of the columns you want stacked together, you provide their names and values. As seen in the example, col2 and col3 are created in two different ways, but they provide the same resulting column of values. Here, scalars are transformed into lists. In this way, you can create a Pandas data frame that contains multiple layers of data with a very simple function. In this process, please ensure that you don't mix lists of different sizes, otherwise an exception will be raised, as shown here. To check the type of data present in each column, check the dtypes attribute. This method is very handy if you wish to check whether a datum is categorical, integer numerical, or a floating point, and its precision. In fact, sometimes it's possible to increase the processing speed by rounding up floats to integers and casting double precision floats to single precision floats, or by using only a single type of data. Let's see how you can cast a type. This example can also be seen as a broad example on how to reassign column data. Col1 changed from int64 to float64. We're now able to import the dataset, even a big problematic one. Now, we need to learn the basic pre-processing routines in order to make it feasible for the next data science step. For example, let's say we want to select all the lines of the iris dataset that have a sepal length greater than 6. We can simply do the following. In the example, we can immediately see which observations are true and which are not, and which ones fit the selection query. Now, let's check how you can use a selection mask on another example. We want to substitute the iris virginica target label with the new label, label. We can do this by using these two lines of code. To see the new list of the labels in the target column, we can use the unique method. This method is very handy if initially you want to evaluate the dataset. You can see that all occurrences of iris virginica are now replaced by new label. The .lock method is a way to access the data of the matrix with the help of row-column indexes. If you want to see some statistics about each feature, you can group each column accordingly. Eventually, you can also apply a mask. The Pandas method groupBy will produce a similar result to the groupBy clause in an SQL statement. The next method to apply should be an aggregate method on one or multiple columns. Grouping observations by target, that is label, we can check the differences between the average value and the variance of features for each group. Later, if you need to sort the observations using a function, you can use the .sortIndex method. Finally, if your dataset contains a time series and you need to apply a rolling operation to it, in the case of noisy data points, you can simply do the following. This can be performed for a rolling average of the values. Alternatively, you can give this command. Instead, this can be performed in order to obtain a rolling median of the values. In both of these cases, the window had 5 sample sizes. More generically, the apply pandas method is able to perform any row-wise or column-wise operation programmatically. As an example of this powerful method, let's now try to count how many non-zero elements there are in each line. As you can see, apply is called directly on the data frame. The first argument is the function to be applied row-wise or column-wise. The second, the axis to apply it on. Note that the function can be built in, library provided, lambda, or any other user-defined function. Similarly, to compute the non-zero elements feature-wise, that is, per column, you just need to change the second argument and set it to 0. Finally, to operate element-wise, the apply map method should be used on the data frame. For example, let's assume you're interested in the length of the string representation of each cell. To obtain that value, you should first cast each cell to a string value, and then compute the length. With apply map, this operation is very easy. The last topic on pandas that we'll focus on is data selection. Let's start with an example. We might come across a situation where the dataset contains an index column. How do we properly import it with pandas? And then, can we actively exploit it to make our job simpler? We'll use a very simple dataset that contains an index column. To make the example very generic, let's start the index from 100. So the index of the row, number 0, is 100. When trying to load a file the classic way, you'll find yourself in a situation where you have n as a feature, or a column. Nothing is practically incorrect, but an index should not be used by mistake as a feature. Therefore, it's better to keep it separated. If instead, by chance, it's used during the learning phase of your model, you may possibly incur a case of leakage, which is one of the major sources of error in machine learning. In fact, if the index is a random number, no harm will be done to your model's efficacy. However, if the index contains progressive, temporal, or even informative elements, for example, certain number ranges may be used for positive outcomes and others for the negative ones, you might incorporate into the model leaked information. That will be impossible to replicate when using your model on fresh data, as the index will be missing. Therefore, while loading such a dataset, we might want to specify that n is the index column. Since the index n is the first column, we can give this command. Here the dataset is loaded and the index is correct. Now, to access the value of a cell, there are a few ways. Let's list them one by one. First, you can simply specify the column and the line by using its index you're interested in. To extract the val3 of the fifth line, indexed with n equals 104, you can give this command. Apply the operation carefully since it's not a matrix and you might be tempted to first input the row and then the column. Remember that it's actually a pandas data frame, and this square bracket operator works first on columns and then on the element of the resulting pandas series. To have something similar to the preceding method of accessing data, you can use the .lock method. In this case, you should first specify the index and then the columns you're interested in. The solution is equivalent to the one provided by the .ix method. Here we'll also get the same output. This method works with all kinds of indexes, labels or positions, and is more flexible. Finally, a full optimized function that specifies the positions, as in a matrix, is the lock method. With it, you must specify the cell by using the row number and column number. The retrieving of submatrices is a very intuitive operation. You simply need to specify the list of indexes instead of scalars. This command is equivalent to the previous one. Alternatively, we can use this line too, and it's also equivalent. This is another way, as is the following command as well. In all the cases, the resulting data frame would be the same.